We are Team Deimos, and this is our URC 2026 System Acceptance Review Submission, introducing our rover, Maurya.
This year, we have migrated from an independent steering mechanism to a differential drive system, enabling us to reduce mechanical complexity and achieve an overall weight reduction of 8 kg, making the rover lighter and more power efficient. In order to activate differential drive, we had redesigned our wheel with two primary function objectives: integrated suspension capability and improved traction performance. Our C section remains same as its core element, allowing the wheels to absorb dynamic forces from the obstacles and reduce the vibrations. The stored elastic deformation energy provides a slight reactive push in the forward direction, assisting obstacle transversal. For optimized lateral and radial traction, we have used triangular thread geometry, reducing slippage and ensuring better torque transmission across uneven terrain. From the past experience challenges in the rocker joint, where inward and outward bending occurred depending on the terrain conditions, this led to excessive stress concentration at the rocker joints and increased torque requirements during the motion. In the updated design, we ensured that both rocker beams remain parallel under all operating conditions. This significantly reduced stress on the chassis and lowers the torque demand for forward and reverse motion. We also redesigned the chassis with high modularity to improve subsystem integration and maintenance efficiency. We repositioned the robotic arm mounting to minimize chassis bending movement. Finally, we optimized the chassis width and rocker length to better suit the differential drive configuration.
This year we have replaced I2C with CAN bus for more noise-resistant communication. We have also migrated from a single combined driver to 4 isolated electronic boxes, each controlling one wheel. The power distribution acts as a 24-volt hub. It uses buck converters for 5 and 12-volt rail and powers a central USB hub for communication with GPS and cameras. The power system features a plug-and-play battery secured in a custom mount with a master kill switch for a secure power cut in case of failure. We are using Jetson Nano as our main onboard compute unit.
For communications, we are using a Ubiquiti Rocket 5 AC Light pair with sector and omni antennas at the base station and rover respectively for reliable communications for up to 900 meters at a 40 MHz adaptable bandwidth, with a new secondary telemetry radio system for reliable out-of-sight communications of odometry and control signals that also acts as a fallback in extreme conditions. A new React.js based GUI for video feed monitoring, mapped environment and GPS coordinate visualization is used to make it easy for the remote operators to operate. This year, we have reworked our entire software stack to take advantage of ROS2 and its associated frameworks. We have incorporated a mathematically fine-tuned spatiotemporal voxel layer for autonomous navigation and IMUs, GPS and optical flow for odometry and localization. For planning, we are using A-Star Global and DWA local planners with new custom recovery behavior, which includes altering SLAM configurations with nav params. For exploratory behavior, such as finding objects or AR tags, we have employed a spiral search based algorithm and the navigation stack for obstacle detection. For Aruko marker detection and pose estimation, we have used OpenCV. We used FastSAM for mallet, bottle and hammer detection due to its flexibility and efficiency, along with item-specific checks such as specific colored pixels or expected sizes and proportions.
We have used 4-bar mechanism for link 1 and link 2 with a noble mechanism that dynamically adjusts the mechanical advantage, give us the high torque for heavy lifting and speed when it's count. For link 3, we relocate the 5th and 6th degree of motor to the rear of link 2. This reduces the self-torque and generating a passive anti-torque effect and improving the energy efficiency. Reaper features 4 degree of actuation with 2 independent figure and a push-pull mechanism enabling adaptive grasping of irregular objects. Additionally, we have introduced an electromagnet-based home locking system that secures the arm during the motion, reduce the vibration and increase the actuator life.
We built a collision-aware manipulation system in ROS2 using MoveIt with a 6G of URDF model. For precision tasks, we enforce Cartesian path constraints to keep the end effector motion strictly linear. We integrated YOLO-based key point detection with depth sensing to ensure reliability during interactions. We implemented a custom pack logic to avoid repeated inputs. Additionally, we use velocity servoing instead of rigid position control, allowing smoother, more compliant motion for dedicated tasks like valve turning and USB insertions.
This year's Life Science module focuses on subsurface regolith analysis and environmental habitability assessment. Soil is excavated to 10 centimeters using a claw mechanism and stored in sealed containers. A unified sensor hub, pH, NPK, moisture, UV, gas, temperature, pressure, and wind sensors interfaces with a Raspberry Pi for real-time data processing. A digital microscope supports microscopic examination.
In our validation, the Bradford assay was conducted on a protein-free soil sample and a protein-enriched soil sample. The control remained brownish while the enriched sample showed a clear blue shift due to Kumasi brilliant blue binding to proteins. The Ninhydrin assay produced Rohemann's purple upon reacting with primary amine groups, confirming the presence of amino acids.
Finally, we extend our deepest gratitude to all our patrons whose support made this endeavor a reality.